Myself, Vishwanagendra Reddy, bearing roll number with 24BQ1804 from the EC department. Today I am saying about a seminar topic about the Boolean algebra. It is a special kind of algebra. It mostly deals with 0 and 1. Here the 0 and 1 are the binary numbers. Binary 0 refers to false and 1 refers to true. In the entire binary systems, just having the only two values, that is 0 and 1. Here in the Boolean algebra uses the some logical operators such as and, or, not. These are the basic gates in the we are using in the Boolean algebra. Here the operation of the and is when the both inputs are one, we get the output as one. Here the at least one input as the one, we get the output as one in the OR gate. Here the operation of the NOT gate is flips the value, it means complement. When we send a 0, it flips, it becomes 1, and we send 1, it becomes 0. It means it is a complement of the input. These are the basic gates we are used in the Boolean algebra. It is mainly used in the digital electronics, such as design circuits. Digital electronics, suppose if you take any electronic component, it is must made up with the circuits. The circuits are made up by these Boolean algebra functions. Next, it is also used in computer sciences and logical gates. In logical gates programming conditions, we are using these Boolean algebra functions. And mathematical and logical reasoning with true or false. These are the basic uses. Basics are the we are using the Boolean algebra. In the Boolean algebra, we have some laws and the theorems. Boolean algebra, these must be follows the conditions. There are some basic laws and rules in the Boolean algebra must be followed. Boolean algebra has to follow some basic laws and theorem. This is known as Boolean algebra. Before going to theorems, laws, we must know the basic operations of the gates as shown in the figure. Here the first one is the AND gate, second one is the OR gate, next one is the NOT gate, and last gate is the XOR gate. Let us see the operation of the AND gate. When we here AND gate has two inputs and one output. Here the input 1, input A, input B. When we send the input A and input B both are 1, we get the output as 1. In the AND gate operation, the multiplication operation happen in the AND gate. Here the dot represents the multiplication of the both inputs. Here the multiplication of both inputs. If we send 1 as input of A, if we send 0 as the input of B, the multiplication of 1 and 0 is output as 0. Okay. Next, when we send the both zeros as the output, we get the input, we get the output as 0. Let's see. Next, for the OR gate. Here the operation of the OR gate is addition of the two inputs. When we send the 0 and 1, we get the input as 1 because the 1 plus 0 is 1. This is the operation of the AND gate, OR gate. Next, for the OR gate, NOR gate. NOR gate means when we send the input as 0, we get the output as 1. When we send 1, we get the output as 0. This is the complement. When we say here, the output represents the A plus, and the same as XOR gate. There A and B are the input for the XOR gate. Operations between this plus and is inserted in the plus circle inserted with plus. These are the operation of the XOR gate. Next, here let us see the truth tables as mentioned in the slide. Here this is the when we send in, there is no AND gate. There is no when we the logic gate which has one input and output represents. When we send 0, we get 0. When we send 1, we get 1. For the OR gate, when OR gate when we get for NOT gate, when we send 0, we get output as 1. When we send 1 as input, we get 0 as output. And for the AND gate, when the both inputs are same, for as 0 and both inputs same. It multiplies means 0 into 0 0, and at least 1 in the both inputs as 1 we get the high. It means high means represents 1, low means represents 0. And for the OR gate, at least one at least one input as 1 we get the output as 1. Here the XOR gate, odd number of ones. When the input as odd number of ones we get output as 1. And for the NAND gate, it is the complement of the AND gate. And also NOR gate is also complement of the OR gate. And XNOR means it is also one type of gate. It is as shown in the figure truth table. and and we have some properties. Properties means x plus 0 is equal to x into 1 is equal to x. Let us see. Let us assume x is equal to 1. 1 plus 0 is equal to 1. Here we taken the input as x and output get as x. X into 1 is equal to x and 1. It means 1 into 1 is equal to 1. It represents the identity law. And for the next one is x plus x is equal to 1. It means we are assumed that x is equal to 1. Here means 1 plus 1 is equal to 1. X into 0 is equal to 0. Anything multiplied with 0, it must always 0. And for the idempotent law means when the both inputs are when we send the both inputs as same to the to the gate. For example, x plus x is equal to x. Let us see. X is equal to 1. 1 plus 1 is equal to always 1. It this operation we are seeing in the OR gate. And next, x into x is equal to x means 1 into 1 is equal to 1. This operation we had seen in the AND gate. These this is called idempotent law. And for the involution law means complement. X complement into whole complement. Let us example. X complement. X complement is, let us we assume as x is equal to 1. 1 x is equal to 1. X complement is equal to x complement whole complement is equal to 0. And for the complementary law, x plus x dash is equal to 1. It means we assume that x is equal to 1. X dash is equal to absolute 0. It means we in a complement, x complement is 0 when x is equal to 1. Means x plus 1 plus 0 is equal to always 1. And for the commutative law means it has the two inputs that is that are x and y is equal to y plus x plus y is equal to y plus x. This is R commutative. The name y is the name y it is called R commutative means the operation between the two gates operation between two gates is OR gate, because this is called as R commutative. And for next one, x into y is equal to y into x. It is called AND commutative. Here y we are called is AND commutative means the operation between the two inputs acts as AND. And associative means we are having the three inputs that is x y z means x plus bracket of y plus z is equal to x plus of plus z is equal to is called associative law. It or associative law. It means the operation between the inputs is OR gate, because it is called OR associative. And next one is AND associative. AND associative means the name it is called AND means product of the inputs. X into bracket of y into z is equal to y x y x dash into y is equal to x dot into y bracket of into z. This is called associative law. And distributive law, it means the x is distributing to the y and z in the distributive law. Here the x into y plus z. It is the multiplication with x. The x is multiplication with y and z between the over the OR gate means x into y plus x into z. The x and y are the operating as the AND gate, and x into z. Here we required one AND gate. These both are distributive with or over the OR gate, and hence it is called as AND distributive over the OR. AND distributive means here AND is distributing through the and is distributing to the x, y plus z, and distributing over the r. It means having the positive, having the plus. Next, here the x plus y plus z, x plus y into z is called x plus y into y plus z. It is r distributive over and same as that one. Here the absorption law. Next one is absorption law. Let us assume x is equal to 1, y is equal to 0. X plus x into y. It means 1 plus 1 into 0. 1 plus 1 into 0 plus 1 plus 0 means it is 1 plus 0 is equal to 1. Here this is called R observative. R observative means here OR gate is performing between the these two inputs, and unobservative means 1 into 1 plus 0. 1 into 1 plus 0 means 1 into 1 is equal to 1. Here 1 means x. This is called unobservative. Next, combining law. Combining law means x plus y plus x into y plus x into y dash is equal to x. Next, x plus y into x plus y dash is equal to x. This is called, these are the Boolean algebra laws. And we go for the theorems. Here we have three theorems. That is consensus theorem, De Morgan's theorem, and next one. And consensus theorem means we have the multiplication of two input, multiplication of pairs of two. Here means x into y, one pair, x bar into z plus x into y into z. These are the three pairs. Three pairs. The sum of the three, sum of the sum of these three inputs is equal to x plus y plus x dash into y. And for the same as we are operating the same as instead of plus we are representing here into means here we are using the OR gate, here we are using the AND gate. X plus y into x bar plus z into y plus z is equal to x plus y into x bar plus z. These are called consensus theorem. And for the De Morgan's theorem, it is a main theorem. De Morgan's law, it is a main theorem in the entire binary system. Wherever we in the wherever whenever we are designing a circuit, it must reduces the reduces the usage of gates. In the when we are using a multiple gates, when we read multiple gates to design a circuit, by using these De Morgan's law, we require a less number of gates. Let us take let us see for example how the De Morgan's law operates. X into y whole complement is equal to x dash plus y. X dash plus y. Here the complement of, here the here the and is coming, getting as a plus, and having the both having the complements. X into y whole complement is called x complement plus y complement. And same as here the and, here we are getting or here and x plus y complement is equal to x complement into y complement. This is about the De Morgan's law. Thank you.